Synthesis, evaluation, and characterization of chitosan and orange peel pellets for nitrate removal in aqueous solution. Introduction. Water pollution is a concerning environmental problem worldwide. This phenomenon originates from both natural and anthropogenic sources. Among the human activities that contribute to this problem is modern agriculture, due to inadequate handling of agrochemicals and poor disposal of waste generated during the production and industrialization process of its products. Nitrate is an agrochemical that, in excess and through leaching, causes contamination of aquifers. Excessive nitrate can have adverse effects on both ecosystems and human health. Health issues associated with elevated levels of nitrate in drinking water include methemoglobinemia or blue baby syndrome, hemolytic anemia, and damage to the gastrointestinal system. The World Health Organization sets the maximum permissible limit of nitrate in drinking water at 50 mg per liter, equivalent to 11 mg per liter of nitrate as nitrogen, using a conversion factor of 0.226. Nitrate can be removed from water using treatment methods such as ion exchange, electrodialysis, reverse osmosis, and adsorption. Adsorption is a fast, low-cost, easy to operate, flexible, highly efficient, and effective process for removing contaminants present in aqueous solutions. Various adsorbent materials have been synthesized for the removal of nitrate. However, some synthesis processes generate byproducts that require special disposal or consume excessive energy, which increases costs and compromises the feasibility of their application. Composites, on the other hand, are adsorbent materials that are formed by combining two or more constituents to generate new physicochemical and mechanical properties in the resulting material. These composites can be created from agro-industrial wastes that act as mechanical support within the matrix by simple synthesis processes, such as ionic cross-linking, that do not generate toxic byproducts. The synthesis of environmentally friendly materials has been focused as an alternative for the sustainable management of waste and its valorization. Orange peel, along with chitosan, represent a viable alternative for the synthesis of composites. Orange peel is a waste derived from the high consumption of oranges worldwide, mainly in the food industry. In 2019, the world production of oranges reached 76.292 million tons, equivalent to approximately 50% of the global citrus production. The generally discarded in open-air landfills and, as they decompose through the action of bacteria, release greenhouse gases, methane and carbon dioxide, that contribute to global warming. Furthermore, chitosan is a linear cationic polysaccharide composed of D-glucosamine and N-acetyl D-glucosamine, linked by beta-14 glycosidic bonds. The use of chitosan in adsorption has garnered significant attention due to its mechanical and physical properties, along with its low cost, environmental friendliness, hydrophilicity, and versatile nature, making it an effective material for environmental applications. The aim of this study was to synthesize biocomposites using chitosan as a polymeric matrix and orange peel as mechanical support. Additionally, to evaluate the impact of pH on the adsorption capacity of nitrate in aqueous solutions, characterize these composites to understand their physicochemical properties, and elucidate the potential mechanism of nitrate adsorption. Methodology. Synthesis of chitosan orange peel biocomposites. The orange pulp and seeds were manually removed, and the orange peel was washed with distilled water and a 0.01 normal hydrochloric acid solution, then dried in an oven at 70 degrees Celsius for 48 hours. The dried orange peel was then ground and sieved to obtain a particle size of 260 to 600 m. The synthesis of chitosan orange peel biocomposites, BCOP, was performed using the ionic cross-linking method, as described below. Chitosan solution was prepared 3%, weight volume, chitosan, acetic acid. A quantity of 4.2 grams of orange peel was weighed and incorporated into the chitosan solution, which was then stirred for 30 minutes. The chitosan orange peel mixture was dripped into a sodium tripolyphosphate solution, 1%, weight volume. After the synthesis was complete, the resulting BCOP were kept in the sodium tripolyphosphate solution for 2 hours at room temperature. Following this, the BCOP was removed from the sodium tripolyphosphate solution and thoroughly washed with distilled water to remove excess. Finally, the BCOP was dried at 40 degrees Celsius in an oven for 48 hours. Batch adsorption experiment. The concentration of the nitrate standard solution was 1,000 milligrams per liter. Dilutions were prepared to concentrations of 10 to 100 milligrams per liter in 50 milliliters volumetric flasks and placed in batch reactors consisting of conical bottom polypropylene tubes. The mass-to-volume ratio of BCOP nitrate solution was 0.1 grams in 40 milliliters. The batch system was then placed in a bath at 25 degrees Celsius until equilibrium was reached. The pH was adjusted to 4, 5, 6, and 7 every 24 hours. The determination of nitrate ions was performed using the select ultraviolet spectrometric method. The amount of nitrate adsorbed was calculated using a mass balance. Characterization of CHITOSAN orange peel biocomposites. The characterization of BCOP and precursor materials was performed using surface and morphology analysis by scanning electron microscopy equipped with an electron dispersive spectroscopy. Textural properties were determined by nitrogen physisorption analysis. Organic functional groups present on the surface of BCOP and precursor materials were identified using infrared spectroscopy. Additionally, thermogravimetric analysis was performed, with a heating ramp of 15 degrees Celsius per minute at 600 degrees Celsius, X-ray diffraction and surface charge distribution, and zero charge point using the method reported by Garcia-Arriaga et al. 2020. Results. Scanning electron microscopy. BCOP micrographs at 50 and 500 magnifications show a rough surface and low porosity figure 1A and B. This can be attributed to the incorporation of chitosan as a polymeric matrix on the orange peel surface as mechanical support, as well as the ratio 1:3 of these components in the BCOP structure. EDS spectrum of BCOP, figure 1C, confirmed the elemental composition: carbon 30%, oxygen 48%, nitrogen 6.6%, potassium 1.2%, and sodium 2%. Nitrogen physisorption. The textural properties obtained from nitrogen physisorption analysis revealed that BCOP has low values for specific surface area, pore volume, and pore diameter at 0.2 square meters per gram, 0.001 cubic centimeters per gram, and 12.8 nanometers, respectively. Figure 2 shows the nitrogen adsorption-desorption isotherm for BCOP, which corresponds to type 3, characteristic of mesoporous materials, and exhibits H3 hysteresis, indicative of mesoporosity. The cumulative pore volume distribution is as follows: micropores 1.97%, mesopores 45.0%, and macropores 52.98%, figure 2b. Infrared spectroscopy, thermogravimetric analysis, X-ray diffraction, and surface charge distribution and zero charge point. Figure 3 shows the IR spectra of chitosan, orange peel, BCOP, and BCOP after absorption. The peaks at 3,435 cm. 1 correspond to hydroxyl stretching and amino overlap. The peaks at 2925, 2875, and 2,854 cm. 1 are attributed to stretching of the methyl groups, methylene and methyl. The peak at 1598 cm. 1 is associated with the NH2 group, while the peak at 1383 cm. 1 shows the stretching vibration of the nitrile group. At 1244 cm. 1 the stretching vibration of the carbonyl ester bond is observed. The peaks at 1068 and 1026 cm. 1 indicate the presence of carbonyl bonds. After adsorption of nitrate, new peaks are observed. The symmetric stretching of the nitrate ion at 1380 cm. 1 and an antisymmetric angular deformation at 830 cm. 1. TGA and DDG curves, figure 3b, show a 4% weight decrease in the range of 20 to 100 Celsius, which can be attributed to water evaporation. Additionally, a 40% weight loss is recorded between 150 and 300 degrees Celsius, attributed to the thermal degradation of cellulose, hemicellulose, and lignin in orange peel. Between 320 and 400 degrees Celsius, an additional 48% weight loss is observed due to the decomposition of chitosan. The XRD patterns of chitosan, orange peel, and BCOP, Fig.3c, did not display well-defined peaks in any region, indicating the absence of distinct mineral phases. Figure 3d shows that the surface charge becomes positive as the solution pH decreases below the zero charge point. This behavior can be attributed to the protonation of the functional groups at the acid sites, lactonic, carboxylic, and phenolic, present on the surface. Conversely, as the solution pH increases, deprotonation of these acidic functional groups becomes possible, favoring a negative surface charge. Nitrate removal. The maximum adsorption capacity of nitrate at pH 4, 5, 6, and 7 at 25 degrees Celsius was 8.9, 7.3, 5.7, and 4.8 mg per gram, respectively. These values indicate an increase in capacity of 1.2, 1.5, and 1.8 times when the pH decreased from 5 to 4, from 6 to 4, and from 7 to 4, respectively, Figure 4a. The adsorption mechanism proposed in this work, Figure 4b, was based on electrostatic attractions between the positively charged amino groups of chitosan and the negatively charged nitrate ions present on the surface of BCOP. This mechanism could also be attributed to the zero charge point of the BCOP, Figure 3d. As seen in Figure 4a, the maximum adsorption capacity was obtained at pH 4, which is lower than zero charge point. At this point, the surface is positively charged, which attracts nitrate ions. Conclusions. The possibility of combining the physical properties of chitosan and orange peel through the synthesis of a composite by the ionic cross-linking method has generated a material with structural and functional properties that make it suitable for use in nitrate adsorption process. The material presents advantages such as low material cost, ease of handling, and higher selectivity compared to conventional physicochemical processes. Acknowledgements. Thanks. The conicet and composite.